Hey everyone, and welcome back to the channel. Today we are going to explore all the JS patterns there is. And first we have the command pattern. Have you ever been working on a big project and you find that one monster class that does everything? It's a nightmare to maintain, and changing one tiny thing feels like defusing a bomb. Today we are going to fix that. We are diving into one of the most elegant solutions for this problem, the command pattern. By the end of this video, you will know how to take that fragile code and transform it into a system that's flexible, scalable, and a dream to work with. Alright, let's look at a classic example. Here we have an order manager class for a food delivery app. On the surface, it seems fine. It has methods to place an order, track it, cancel it, add special instructions. But it also has methods to get history, print receipts. This is what's known as a God object. It knows too much and does too much. The real problem here is a tight coupling. Any of our app that wants to place an order has to know about the order manager class directly. It has to know the exact method name, like place order. If you decide to refactor that to add order, boom, you have to hunt down and fix every single place you called it, and your app breaks. There has to be a better way, and there is. The solution is encapsulate every single action into its own object. Instead of calling methods directly, we are going to create and dispatch commands. This is the blueprint for the command pattern. It has 4 key players. Watch as they build out. First, the client, which is the part of our app that needs something done. Instead of talking to the business logic directly, it creates a command and gives it to an invoker. The command object itself contains all the information needed to perform the action. And finally, the command knows how to talk to the receiver, the object that actually does the work. See the beauty of this? The invoker has no idea what the command does or who the receiver is. It's completely decoupled. So, how does this look in our code? We start with our cluttered order manager, and with this command pattern, we refactor it into this. Beautiful. It's now simple invoker. It has only one job: to exaggerate any command it's given. It's clean, simple, and follows the single responsibility principle. So where did that all logic go? It went into our new command objects. We can start with a simple command interface, then each action becomes its own factory function that returns a new command instance. Here's a place order command. It takes the order details and returns a command object containing the exact logic for placing an order. We do the same for tracking, canceling, or any other action we need. Each one is a self-contained, isolated unit of work. Alright, this is the best part. Let's see it all come together in a live scenario. On the left is our client code, and on the right is a live dashboard of our orders. First, the client exaggerates a place order command for some pad thigh. Perfect, the order appears. Now let's exaggerate an update status command. The dashboard updates instantly. Let's track it again, and finally let's say the customer changes their mind about a different order. We exaggerate the cancel order command. Look at that. Our client code is clean, declarative, and completely separate from the system doing the work. This is incredibly powerful, but decoupling is just the beginning. This pattern unlocks some serious superpowers for your application. Because each action is an object, you can easily implement undo and redo. You just store a history of commands and call an undo method on them. You can create queues. Need to make sure a bunch of database operations happen in a specific order, but the command in a queue and exaggerate them one by one. You can even schedule them to run later. And finally, logging. You can easily save a history of every command exaggerated, creating a perfectly audit trail for debugging or analytics. And that's the command pattern. It's a fantastic way to clean up your architecture, reduce bugs, and build systems that are a joy to scale and maintain. By turning requests into objects, you open up a whole new world of possibilities. Take a look at your code. How often do you find yourself creating the same type of object over and over again? It's a common task, but doing it manually is a recipe for disaster. Today we are going to replace that manual labor with a powerful automated assembly line for our code. We are going to master the factory pattern. Let's start with a scenario we have all seen. We need to create a couple of user objects. Each has a first name, last name, email, and a method to get the full name. We just copy, paste, and change the values. But notice the problem here, the structure is identical. The full name method is duplicated in every single object we create. If you make a typo in one or forget a property, you have introduced a bug. This doesn't scale. The solution is beautifully simple. We create a factory function. Its only job is to receive raw materials, our data, and reliably produce a perfectly formed object every single time. The transformation looks like this. Instead of a messy repeated object literals, we define one clean, reusable function called createUser. It takes in user data and implicitly returns a new object with the correct structure. The new keyword, no complex constructors, just a plain function that acts as our object. Factory. Now creating user is as simple as calling our new function. And here's where the magic happens. On the left is our factory code, on the right is our list of manufactured objects. Let's start the assembly line. First, we call create user for John Doe. The data goes into the factory and comes out a perfect user object. Let's do it again for Jane Doe. The data goes in and another perfectly structured object is produced. This is the core of the factory pattern. Single reliable source of truth for object creation. But there is a critical detail we need to talk about: memory. With this simple factory, every object we create gets its own copy of the full name method, or thousands of objects that can add up. This is where the alternative, a class, shines. When you create instances from a class, they don't get their own copy of the methods. Instead, they all share a single set of methods from the class prototype. This is far more memory efficient. So, which one should you use? It's a classic trade-off. You should use a factory when you need to create a lot of simple objects, or when the object's shape might need to change based on the input. It's also great if you want to avoid the complexities of this keyword. But you should consider using a class when you're creating many large complex objects and memory efficiency is top priority. It's also the clear choice if you need features like inheritance. Understanding these trade-offs is a key to writing professional high-performance code. The factory pattern is an incredibly useful tool for keeping your code clean, simple, and predictable. In modern software, it's not uncommon to deal with thousands or millions of objects at once. A game might need to render a million particles. A spreadsheet might have millions of cells. If you're not careful, this is the fastest way to crash an application. Today, we are going to learn the secret to managing this scale efficiently. This is the Flyweight pattern. Let's start with a problem. Imagine we are building an app for a library. We need to represent every single physics book on the shelves. The naive approach is to create a new complete object for every single copy. Here's one copy of Harry Potter. It has a title, author, ISBN, and its availability. And here's the second copy. Look at all the duplicated data. The title, the author, the ISBN, it's all identical. We are storing the same strings over and over again. Now multiply this by 5,000 copies. You can see how this quickly becomes a massive waste of memory. The core idea of Flyweight pattern is to split our objects data into two distinct types. First, there is the intrinsic state. This is the data that is shared among many objects for our book. This is title, author, and ISBN. This shared object is called the Flyweight. Second, there is the extrinsic state. This is the data that is unique to each individual object. Its context for our book copy, this would be its availability, its specific condition, or its location on the shelf. To manage this, we first build a Flyweight factory. Its job to ensure that we only ever create one shared Flyweight object for each unique book. Its simple function called createBook. When we ask for a book, it first checks a cache, in this case a map, to see if we have already created a Flyweight for that ISBN. If we have, it returns the existing object instantly. No new memory allocated for the shared data. If we haven't, if it creates a new book object, stores it in the cache for future requests, and then returns it. This guarantees we never have duplicate Flyweights. Now let's pull it all together. On the left is our application code, which uses an addBook function to combine the shared Flyweight with the unique data. On the right, you will see our Flyweight cache and the final library shelf. First, we add a copy of the Harry Potter. The factory sees its new ISBN, so it creates a new Flyweight in the cache and the unique book copy appears on the shelf. Now let's add a second copy of Harry Potter. Watch the cache. Nothing new is created. The factory simply reuses the existing Flyweight we have saved in memory. Let's add two couples of To Kill a Mockingbird. One Flyweight, two copies, and one Great Gatsby by the end. We have 5 unique book copies on our shelf, but we only ever stored the shared data for 3 books in our cache. That's the power of the Flyweight. But this pattern isn't free. It represents a classic engineering trade-off. You're trading a little bit of CPU time for a lot of RAM. The benefit is obvious. Massive memory saving. This is absolutely essential for high-performance applications that handle huge numbers of similar objects. The cost is a slight increase in complexity and CPU cycles needed to look up the Flyweight in the cache every time you request an object. So, is it worth it? For a huge dataset, absolutely. For a handful of objects, the overhead isn't justified. And that is the Flyweight pattern. It's clever memory saving techniques that is crucial for building scalable high-performance applications. By thinking carefully about what data can be shared, you can make your programs run more efficiently on a massive scale. One of the hardest problems in software is managing how components talk to each other. As an application grows, you can end up with a chaotic web of connections where everything depends on everything else. Today we are going to fix that. We are going to implement an air traffic controller for our code using the Mediator pattern. This is the nightmare scenario. Each component here is communicating directly with every other component. This is called high coupling, and it makes your system incredibly fragile. If you need to change or remove just one of these components, you risk breaking the entire application. The solution is to cut these direct lines of communication. Instead of a chaotic free-for-all, all communication now flows through a central hub, the mediator. Components no longer know about each other, they only know how to talk to the mediator. Think of it like an air traffic controller. Pilots don't talk to each other to coordinate landings. They talk to the control tower. The tower, our mediator, has the full picture and directs traffic, ensuring everything runs smoothly and safely. A classic example of this pattern is a chat room. Here, the chat room class is our mediator. Its only job is to receive a message and log it. The user class is a colleague. Notice that when a user sends a message, they don't send it to another user. They call this .chatroom.log message. They only communicate with the mediator. Let's see this in action. On the left, we have our users, John and Jane. On the right is a chat window controlled by our mediator. First, John sends a message, he passes it to chatroom, and the chatroom displays it. John has no idea if Jane or 100 other users are even in the room. Now Jane replies, same process, this is a loss of coupling in purest form. Now let's look at a specialized linear version of this pattern that you have likely already used, middleware. This is a famous in web servers like Node.js with Express. Instead of a central hub, middleware forms a chain or a pipeline that requests must flow through. Each function in a chain can inspect or modify the request, and then it calls next to pass control to the next function in line. Here is our middleware pipeline. A request object is about to enter. It hits the first middleware gate. The function adds a custom header to the request object. You can see the indicator on our request object turned green. It then calls next. The request arrives at the second middleware. The one's job is to check if the header from the previous step exists. It finds it, logs the message, and calls next again. Finally, the fully processed request reaches the route handler, which sends the response back to the user. This clean, predictable flow is made possible by the middleware pattern. So, why go through the trouble of setting up a mediator? Two huge reasons. First, loose coupling. Components are completely independent. You can add new chat users or new middleware functions without ever touching the existing ones. And second, centralized control. All the complex interaction logic lives in one place, the mediator. This makes your application dramatically easier to understand, debug, and maintain. By preventing a tangled web of communication, the mediator and middleware pattern allow you to build complex systems that are robust, flexible, and scalable. It's a fundamental technique for professional software architecture. In object-oriented programming, we are taught to use inheritance to share functionality. A dog inherits from animal, which inherits from living thing. But this can create rigid, complex chains that are hard to change. What if you want to give an object a power that doesn't fit neatly into that hierarchy? Today, we are breaking free from those chains. We are going to explore a powerful technique for code reuse called the Mixin pattern. Let's start with a simple dog class. When we create an instance, it has a name, and that's it. It's a lifeless object. It can't spark, it can't play, it can't do anything. On the left, we also have this simple object literal called dog functionality. Think of it as a bag of powers or a blueprint of abilities. How can we give this power to our dog? This is our Mixin. It's just a plain object that holds the methods we want to add. The solution is to inject this functionality directly. We are not going to use inheritance. Instead, we are going to mix these new abilities right into our dog class's DNA, so to speak. We achieve this with a built-in JavaScript method, object.assign. Its job is to copy properties from one or more source objects to target object. Here's the magic line. We target the dog.prototype, the shared blueprint for all dog instances, and copy the methods from our dog functionality Mixin onto it. Now let's visualize this infusion of power. Here's our Mixin blueprint. When object.assign is called, the functionality is copied over. The prototype is now energized with these new methods. That means every single instance of dog, including the one we just made, instantly gains these new abilities. Now when we call pet1.bark, it works. Let's try wagtail and play. We have successfully added reusable functionality without a single extends keyboard. This pattern is incredibly flexible, but it comes with a serious warning label. It's powerful, but it can also be dangerous. The huge advantage is code reuse without the inheritance. You can share abilities between completely unrelated classes. A dog and a car could both have a wash method from the same Mixin, even though they share no common ancestor. The massive downside is called prototype pollution. Modifying an object's prototype directly is often considered a bad practice in large applications. It can lead to unexpected behavior and make it very difficult to know where a functionality is actually coming from, which is a nightmare for debugging. It can also lead to name collisions if two Mixins define a method with the same name. Because of these risks, modern JavaScript frameworks like React have moved away from Mixins, preferring patterns like hooks that favor composition. So, the Mixin pattern is a powerful tool to have in your arsenal, especially for quick, flexible solutions. But like any powerful tool, you have to know when and when not to use it. When you click a button in an application, a dozen different things might need to happen. A log needs to be written, a notification might pop up, a counter could increment. How do you manage all that without turning your buttons code into a complete mess? The answer lies in one of the most important design patterns in all software engineering, the observer pattern. This is the code we want to avoid. In this handle click function, the button itself is responsible for everything. It's tightly coupled to the logger, the notification system, the counter, and the analytics server. If you want to add a fifth action, you have to modify the button's code. If you remove the notification system, you have to remember to delete the line or the app will crash. This is not maintainable. The observer pattern flips this model on its head. The object where the event happens, we will call it the observable, has only one job: to shout to the rest of the app, hey, I was just clicked. Other parts of the application, the observers can choose to listen to that shout. The button doesn't know who is listening or if anyone is listening at all. It just sends the signal. We can implement this with a simple observable class. It's the central switchboard for our entire system. It has a subscribe method which allows any interested observer to add itself to a list of listeners, and unsubscribe method to remove itself from that list, and most importantly, a notify method. When called, it iterates through its list of observers and fires off the notification to every single one of them. Let's build a real example. We have two simple functions that will act as our observers, a logger and a toastify function. To make them listen, we need to subscribe them to our central observable. First, we subscribe the logger. A connection is now established. Then we subscribe our toast notification handler. Now both of these functions are listening, waiting for the signal. Now for the payoff, when I click this button, the handle click function calls notify the observable, broadcast the event, and both of our observables react independently. The logger logs the message and the toast appears. Let's try the toggle. The exact same thing happens. The component that fires the event is completely decoupled from the component that handles the fallout. This is clean event-driven architecture. So, why is this pattern so fundamental? First, separation of concerns. The observable's only concern is to report that if an event occurred. It doesn't care that what happens next. The observer's only concern is to react to that event. This makes your code incredibly clean and easy to reason about. And second, dynamic relationships. You can add or remove observers at any point during the application's lifecycle. Need a new analytics tracker? Just subscribe a new function. Is the user in do not disturb mode? Unsubscribe the notification observer. It's incredibly flexible. This pattern is the foundation of almost all modern UI frameworks and reactive libraries like RxJS. By decoupling the what from the who cares, the observer pattern allows you to build complex reactive systems that are easy to extend and maintain. It's one of the most valuable patterns you can have in your toolkit. To truly master JavaScript, you have to understand how it works under the hood. It's not about frameworks or libraries, it's about the native features of the language itself. and there is no feature more fundamental to how objects work than the prototype. Today we are pulling back the curtain on JavaScript's native inheritance model, the prototype pattern. Let's start with what we don't want to do. Imagine a function that creates a dog object. In this example, the bark function is part of the object that gets returned. This means that if we create 1,000 dogs, we are also creating 1,000 separate copies of the exact same bark function in memory. This is incredibly inefficient. JavaScript solves this problem with an elegance. Instead of duplicating methods, it stores them in a single central object, the prototype. Every instance we create doesn't get a copy. Instead, it gets a live secret link to that shared blueprint. Modern ES6 classes makes this pattern incredibly easy to use. In fact, they are often called syntactic sugar because they provide a cleaner syntax for this understanding prototype mechanism. When you define properties inside the constructor with the this keyword, those properties belong directly to the instance itself. But when you define a method on the class, JavaScript automatically places it on the shared dog.prototype object. It's not copied to each instance. This creates what's known as the prototype chain. Let's build it out. At the bottom, we have our instance dog1. It has own name property. It has a secret proto link that points up to the dog.prototype. This is where the shared bark method lives. But dog.prototype is just an object, so it also has proto-link which points to the base object.prototype. This is where universal methods like toString live. This is the chain. Now watch what happens when we call dog.bark. JavaScript first asks, does the dog1 instance itself have a bark method? No, it only has a name. So it travels up to the prototype chain. It asks, does dog.prototype have a bark method? Yes, it does. The search is over, the method is found, and the code is exaggerated. This is how all instances can share one method. You don't even need classes to use this pattern. The object.create method gives you a direct control. Here we have a simple object dog with a bark method. We can then create a new completely empty object called pet1 and explicitly tell JavaScript that its prototype should be dog object. Pet1 has no properties of its own, but because of the prototype link, it can still bark. So why is understanding this is so critical? First, memory efficiency. This is the core reason it exists. By defining methods only once, JavaScript applications can handle thousands of objects without running out of memory. It's fundamental to the performance of the web. And second, the link is dynamic and live. If you add a new method to a prototype after your instances have already been created, they will all instantly gain access to that new method. It's powerful and sometimes dangerous feature of the language. The prototype pattern isn't just a design pattern, it's the very essence of how inheritance and object interaction work in JavaScript. Mastering it means you're no longer just using the language, you're understanding it on profound level. Normally, when you interact with an object in JavaScript, it's a direct connection. You ask for a property, you get it. You set a property, it's set. But what if you could put something in the middle? A gatekeeper that lets you see and control every single one of those operations. This isn't a hack, it's a powerful built-in feature of the language. This is the proxy pattern. This is the standard flow of traffic. Your code has a direct line to the target object. This is simple, but it offers zero control. We can stop someone from setting an age property to a string of nonsense. You have no way of knowing when a property was accessed for debugging. It's black box. The proxy pattern fundamentally changes this relationship. It allows us to wrap our target object in a stand-in or a proxy from now on. Our code will only talk to the proxy. The proxy in turn will manage all access to the real object, giving us the power to intercept and redefine these basic operations. We create a proxy by passing our target object and the handler object to the proxy constructor. This handler is where we define our traps. The two most common traps are get, which fires when a property is read, and set, which fires when a property is written to. Now let's watch this guardian in action. When our code tries to get the name property, the request is fired. The proxies get the trap, intercepts it, runs our custom console.log, and only then retrieves the value from the real object. Now when we try to set the age property, a different request is fired. The set trap catches it, it logs the change, and then performs the actual update on the target object. We are now in complete control of the flow of data. This control is incredibly incredibly useful for data validation. Our set trap can act as a gatekeeper, checking a new value before they ever touch our real data. Let's try to set the age to a string. The proxy intercepts the operation, sees the data is invalid and returns false, rejecting the change completely. Our original data is safe. Now let's try a valid change. The data passes the validation check and the proxy allows the operation to process. This is how you build truly robust objects. While accessing the object directly inside our traps works, JavaScript provides a cleaner, more robust way. The built-in Reflect API. Reflect has methods that perfectly mirror the proxy traps, like reflect.get, reflect.set. This is considered best practice as it handles certain edge cases more gracefully. So, when should you reach for a proxy? It's your go-to tool. Anytime you need to control or observe interactions with an object. It's the foundation of data validation, logging, and is used heavily in modern frameworks to create reactive systems, where the UI automatically updates when the underlying data changes. However, this power comes at a small cost. This layer of abstraction means that accessing a property through a proxy is inherently slower than accessing it directly. For this reason, you should avoid using proxies in higher performance critical code, like a loop that runs thousands of times a second. The proxy pattern gives you an unprecedented level of control over the fundamental operations of JavaScript. It allows you to build smarter, safer, and more reactive objects. It's a modern feature of the language that every serious developer should understand. There is a design pattern that promises the ultimate control, a class that can only be instantiated once, a single globally accessible object that holds a state for your entire application. It's one of the most well-known patterns, but also one of the most controversial today. We are directing the Singleton pattern. Let's first understand what makes it unique. Normally, when you create instances of class, you get a fresh independent object every single time. Instance 1 and instance 2 here have no connection to each other. The Singleton pattern breaks this rule. It's designed to ensure that no matter where or when you ask for an instance, you always get back the exact same one and only object. So, how do we enforce this rule? The trick is to use a private variable to hold the instance. Inside the constructor, we check if the instance variable has already been set. If it has, it means we are trying to create a second instance, so we throw an error to stop it. If it hasn't, we set the instance variable to this, the new instance we are creating. Finally, we create that single instance, freeze it to prevent accidental changes, and export it. From this point on, the entire application will share this one object. This is where the Singleton primary use case comes into play. Managing global state. Imagine the central core is our Singleton counter, different module in our app, like redbutton.js and our bluebutton.js can import it. First, the redButton module imports the Singleton, establishing a connection. Then a bluebutton does the same. Both are new, plugged into the exact same power source. Now watch what happens when they interact with it. The red button's event handler calls increment. The value on the single shared instance goes up. Now the blue button calls increment. The counter doesn't start over. It continues from where the red button left off, because they are both modifying the exact same object. This is shared state in action. This seems useful. So why in the world of JavaScript is the singleton often called an anti-pattern? There are three major problems. First, singleton are essentially global variables in a fancy trench code. Global state can be dangerous because it can be modified from anywhere, at any time, leading to unpredictable behavior and bugs that are incredibly hard to trace. Second, they create tight coupling. Any module that imports the singleton is now permanently dependent on it. You can easily replace it with a different version for a test, for example, without changing the code that uses it. And that leads to the third problem: they are difficult to test. Since you can create a fresh, clean instance for each unit test, your tests become dependent on the state left over from previous tests. This makes your test suite fragile and unreliable. In many other languages, classes are the only way to create objects, so this pattern makes more sense. But in JavaScript, we can create objects directly. All that class boilerplate is overkill. A simple object exported from a module achieves the exact same goal because of how ES modules work. Every time you import this file, you get a reference reference to the same object. It's natural, simpler, cleaner singleton without the class baggage. So while the singleton pattern is a classic you should know, in modern JavaScript, it's often a sign that you might be creating a global state problem. The language itself gives us a simpler, more elegant ways to achieve the same result. If this deep dive into all JavaScript patterns was helpful, a like and subscribe is always appreciated. Thanks for watching.